Well, let me try to explain question 7 section 3.8, 3.8, and 3.9 about non-level payment. I tried this question myself, one version of it on my try on my version of it. So when I try it on your version, it will make more sense. I mean, with more example, we'll see if we understand the underlying reasoning. The question is about a perpetuity, so let me erase what I did earlier. I have to try it just so we will not waste time. Okay, so today, so that t equal to 0 is representing January 1st, 2003. Okay, but there's no cash flow, so the present the cash flow at time 0 is 0. Then the first payment is January 1st, 2009. So if you count number of years, that's already t equal to 6. 9 minus 3, t equal to 6. The amount of the payment is 4,000. You can make it negative or positive along the timeline, but let's consider that being positive for A40. And then after that, each payment, including the one on January 1st, 2035, is 4.5% larger than the previous payment. So this is a geometric series as far as the value of the payment. That is the last one following this pattern is January 1st, 2035. So if you take 35 minus 3, it will be 32. So that's when t equals 32. To count the timeline. And then that last payment will be, there has to be a couple of payment here. Now each payment is 4,000 and 4840 times, it says 4.5% larger, so that means it is 1.045 of the one before, and that's depend on the number of years. So that has to be whatever year that is minus, say, I'm thinking about the value, minus 2009. For example, in 2010, it will be 2010 minus 2009, which is you multiply one of the factor 1.045. Let me just write that. Okay, so the last payment must be 4840 multiplied by 1.045 to the power of the year is 2035. You minus 2009 is 26. So last payment has power of 26. Okay, and then from then on, it become a arithmetic sequence. After that, the payment increased by 300 annually. So then this is a perpetuity. We're assuming the payment continue. So for example, at t equal to 33, then the payment is going to be, the cash flow is going to be the one earlier plus 300. And after that, t equal to 34, then the payment will be the one before plus 30 again. Okay, for this, the textbook already have a formula for this, but if you want to, you can also draw the timeline. So if you want a visual picture of what's going on, you can also draw a timeline for, and that is, this is 2000, 2003. And the first payment comes at 2009. And if follow cash flow is 4840, and then at 2010, the payment become 4840 times 1.045, and then continue from there. The last one that follow this pattern is at 2035. If the payment must be 4840 times 1.045 to the power of 26. Okay. If we call this value A, the payment value, then the payment after that would be, so the year after 2035 is 2036. The payment must be A plus 300, and then A plus 600, A plus 900, and so on. So what I did, I think you probably do the same thing. Let's identify the timeline. This is time equal to 0. This must be time equal to 6. And this is when the time equal to 32. Because you take 35 minus 2003. All right, so we can then find the individual total value. So you can actually find the total value for the geometric series, which is this one. All right, the total value, if you find its value at t equal to 6 value, so t equal to 6, the value, this is the time value, its value at t equal to 6. If you want to find the present value, you have to discount it to t equal to 0. But right now, let's try to apply the formula. So at t equal to 6 is the value, t equal to 6 value is equal to, at t equal to 6, or at 2009, the value, the 4840 is that first payment. And then after that, we have 4840 times 1.045, because that's a increasing payment. But this increasing payment has to be discounted by the time value. That's 1.069. That was the interest rate that was quoted in the question, and it follows the same thing. And then the next one is 4840 times a 1.045 over 1.069. And we have to do this for all the payment after that until the last one, that was the 4840 times 1.045 over 1.069. And you can see that clearly this is a geometric series. The last one has a power of 26. Okay, following the geometric sum formula in calculus, this is equal to 4840 being a common factor multiplied by 1 minus, I saw your formula, you have a similar formula like this, over 1.069. And this factor multiply to the power of 27, because that's how many terms we have in the series, in this partial sum. And then this is divided by the 1 minus the ratio, that is 1.045 over 1.069. Right, that's the t equal to 6 value for the geometric series payment. And then after that, at t, we can find, we have we can find the value of the rest of payment. Instead of directly calculate what is value at t equal to 0, we can temporarily, for the sake of applying the formula, we can calculate what is the value at t equal to 31. Because the first payment is 4840.1045. No, the first payment is A plus 30. Right, since the rest value is already added. Right, so the first payment should not count that one. That is gonna be a problem. So there are the rest of the payments. So the first one, let's see if it makes sense. So if we're using the annuity immediate formula, what we are calculating its value at t equal to 32 instead of 31. All right, so according to the increasing payment formula that you see in the text, so the A, you pay A plus 300, A plus 600, A plus 900, A. So it's like having a annuity that has a quantity A, as perpetuity. So for that part, it's gonna be, the A is 4,440 times 1.05 to the 26th power. So the first payment is A plus 300. And then after that, so A plus 300 is in every single payment of this, and then plus the increment. I is a formula, but the actual value of I is a interest rate is 0.069. After that is the increment of 300. So 300 is divided by I squared. That is 0.069 to the power of 2. Okay, that's following. If we want to quote, you can look at the formula that we learned in the second part. It's also in the text, but I can find it pretty quickly in here. All right, so 3.6 is when we start introducing all these new formulas. You can, even if for geometric theory, we might have to think about geometric formula, but for arithmetic and kind of payment, we can actually separate them into different annuity. All right, for this one, there's this formula. Okay, so this is where increasing payment, initial payment being P, then the increment being the value of Q. So we have P times this plus Q over I times this. But then when it's in perpetuity, then the the extra term actually will be canceled, right? It's easier with this formula, right? So you can see that when the n it goes to infinity, this is P times 1 over I, and Q over I times 1 over I, so it's just Q over I squared. And I guess we have a combined formula here. One of the example is directly, this is a formula. It's 3.9.16. That's the one I'm using. Let's see. But then we have the red part and the green part, we have to discount it to times 0. So total value at t equal to 0, we discount both of them. So the first one will be, let's total them. The first one will be 4840 times 1 minus 1.045 over 1.069. And this factor raised to the power of 27. This is divided by 1 minus 1.045 over 1.069. And then we discount with the negative power, it's times 1.069 to the power. This is t equal to 6 value, so we raise to the power of -6. The second one, 4840 times 1 minus 1.045 over 1.069. I think I wrote the wrong thing. All right, it's supposed to be 8 times 1.045 to the power of 26 plus 300. This is over 0.069 plus 300 over 0.069 to the power of 2, discounted for 1.069 to the power of 32. Negative 32 discount factor. So the answer is supposed to be I tried it earlier. Problem with princess. Okay.